Hello, everyone. Thank you for coming. My name is Isaac Murchie. I'm the chair for today. Our first speaker is Katherine Scott, and since we're a little bit late, we'll ask for no questions at the end, but you can meet her at the back. She also has to kind of clean everything up, so she'll be at the back at the end of her talk, so if you want to ask any questions or continue the discussion a little bit. Okay, so Katherine Scott.
So let me just set this up real quick. Is everyone having fun this morning? Excellent. Hey, wonderful. All right, so I am here, well, first off, I'm Katherine Scott, and I am here to talk to you guys about robots, and specifically ROS. So why should you listen to me? So I've been doing this for like going on 15 years now. Started off in undergrad working on this robot, which is a legged robot that's it's called Rex. Went to a defense contractor who basically did a lot of robotics work and automation work. Oops. Uh-oh. Yes, keep this configuration. All right, and then went on to build a robotic car, and then also hung out and did some first robotics work. Presently, I'm actually building a robot that does quick turn pick and place for PCB assembly. So this robot, what it does is it basically takes these little tiny components right here, and it places them on circuit boards. So they're robots that do this already, but they're all optimized to build like a million of something. So I'm actually building a robot that's a lot smarter than those robots and takes, only a few minutes to set up versus a few days, so you can actually develop prototypes a lot faster. And so the shameless plug here is that I build these boards. If you have boards, let me know. I might be able to make them for you, and I'm also looking for engineers. All right, so before we talk about robotics, why don't we talk about the web? So most of you, when you want to go build a website or do something like that, you don't go and try to do everything from first principles. You don't, start looking at Socket.io and how do I talk over the internet and everything like that. You just sort of pop into Flask and do what you want to do. So when I talk to people about robotics, what I normally end up hearing is, oh, well, I rolled this from scratch, I rolled that from scratch, I figured this out from first principles, I figured that out from first principles. We shouldn't have to do this. We shouldn't have to reinvent the wheel to do robotics work. And it turns out you really don't have to. There is this awesome robotics package called ROS. And what ROS is it's basically Robot Operating System. So it's a set of packages primarily for Linux, works really well in Ubuntu, also works really well in ARM, that allows you to quickly and easily build robots from scratch. It has a huge and wonderful open source community. It is reasonably mature and battle hardened. It's been running on, robots like Baxter and all sorts of different research robots, but also things in production. And it's really, really light and flexible. So it allows you to basically intersperse C++, Lisp, Java with Python with great ease, and then it also allows you to add in some Java and JavaScript support. So what is it internally? So internally, ROS is basically a package manager, and a lot of that's apt. So I can apt-get one of thousands of robotics packages for cameras, camera drivers, all sorts of stuff like that. It is also a build system called Catkin, and so Catkin basically allows you to do all this C++, Python, Lisp interspersion. And then it's also a deployment system or launch files. So if I have this big, huge robot system, it allows me to bring stuff up, bring stuff down, restart it, all of that. Underneath of all of that, I like to think of it as a publish-subscribe system, basically a messaging bus. So ROS sits there, it spins stuff up, and it allows these independent little nodes inside of your robot to talk to each other by either publishing or subscribing to a message. On top of all of this, what you get for free is basically every utility you could ever imagine. Logging. You can log just about everything, and log data, lots and lots of data. I've logged terabytes and terabytes of data in a single evening on ROS. You can replay that data. You can introspect that data. You can, go through log files and look strong. It's just tons and tons and tons of tools that you could use every day. And finally, there's just lots of standard libraries allowing you to do so many different things. So there's libraries for handling image processing, for handling inverse kinematics, for handling 3D modeling, for running various, various weird servos and that sort of thing. So I can sit here and I can talk about everything all day, or we can actually do some fun robotic stuff, which I think you guys would rather see some code being written and deployed rather than me just chatting. So if you will notice up here, I have this little guy. This is Twitchy. I picked him up for like $100 on Amazon. He's just a little 4-axis arm. This is called a palletizing robot. And so this Twitchy is really just a miniature model of something like this KUKA arm here that's used in manufacturing settings to do palletization. So palletization is when you get this giant pallet of cereal. This robot puts all the cereal on that pallet before it gets shipped out. They're super cool. So what is running my friend Twitchy here? So Twitchy is just really 4 servos. So underneath, there's not a whole lot of magic here. There's just an Arduino and basically a little tiny shield. And all the shield is doing is giving me a place to plug my motors into, and it's shunting current from a higher voltage source. That's it. And there's also a kill switch. So you need to have a kill switch, and it's not because the robots are going to take over. It's because any robot, I don't care how big or how little, can either hurt you or hurt yourself. So always, always, always put a kill switch on your robot. All right, so you guys want to see ROS in action and see how it plays out? Okay, so all the prerequisites I did to get this running are basically I installed ROS Indigo desktop on Ubuntu. I installed something called ROS Serial, which will allow me to talk to this guy. I set up a Catkin workspace, so Catkin's the build environment, and there's lots of tutorials that'll walk you through that. I downloaded the Arduino IDE, and I set up for ROS, which basically means running a Python script to copy some files over to the Arduino IDE. And then I loaded some source code. All right, so for this first step, what we're going to do is we're going to have the Arduino learn to talk to ROS. And so what the Arduino will do is it will publish a topic. So it'll publish a topic called state, and state is just 4 integers, one corresponding to each motor's position on here. And then it'll also listen on a topic for messages that are called robot. And that's just where we say, robot, I want you to go to these 4 positions. So just to make this perfectly clear, robot listens for state, updates its state, sends out a message echoing the same thing. And then I added a second node that basically publishes a human-readable message. And so what's great about all of this is that ROS will handle all of that message passing for me. I don't have to think about it. I can just do it as a given. All right. So if you guys will bear with me, are we okay looking at a little bit of C for like 1 minute? I'll show you how this works. Last bit of C, everything else will be in Python and XML. So here we go. It's basically import some ROS libraries. Import a int16 multi-array message, which is just what's going to be holding those integers that we move back and forth. And then also a string message, which is just a message in a string. And all I do inside of this Arduino is I say, ROS, there's going to be a node, which is going to wrap all of this stuff. There's going to be messages like of that 4 int kind and also of a string. And I say, hey, I'm going to publish the state message. I'm going to publish the status message. So then you spin up your servos right here. You clip the values that are coming into and out of the servos. And then I'm going to set up a callback. And this callback is basically, whenever you get this robot message, whenever you get this thing that says, go here, you make the servos go here. And so this is where that callback gets set. Then we do your standard Arduino thing where we set up and attach all the servos. And then we basically initialize everything to 90 degrees, make the servos go there, and spin up all of our ROS stuff. So we set the baud rate, initialize the node, subscribe to the robot topic, and advertise that we are publishing a state and status topic. And then, finally, in our Arduino update loop, we go through and we say, oh, here's the status of the robot. Make this a string and publish it out. So you guys got that? Does that make sense? Kind of? All right, so we'll spin this up. Just gotta plug this in. All right, so that's running. I guess we should upload it just for good measure. So if we wanted to launch this and have ROS on my desktop connect to what's running on here, we have to run ROS on my machine. So to do that, what we use is called a launch file. So launch files are basically piles of XML that allow you to deploy bits of code. It allows you to start nodes, change nodes names, change topic names, set parameters, all the sort of stuff that you would put in, like, say, a bash shell to go start up a program. And so you can also sort of build hierarchies of these. So if you have a whole camera subsystem on your robot, you could deploy just the camera subsystem as a single file being pulled in by launch file. So in this case, what we see here is the launch file for the serial controller is just, hey, there's this thing called raw serial Python. I want you to start the serial node, name it Arduino serial. It's going to be on this port and have this bot. So what we can do is we can do ROS launch, serial controller, and surprisingly, nothing will happen because we haven't told the robot to do anything yet. But what we can do is we can write a little program that says, oh, hey, I know that there's this robot controller on the serial connection, tell it to do something. So this is Python, back to Python. What we do here is we import this sort of array message. You see this int16 multi-array. Same thing that we used on the C++ side. We can import that as an object. And we spin up this little Python program. We say, I'm going to call this simple publisher. I'm going to publish to the robot. So this is, on the robot, this is what takes in those 4 ints. I'm going to publish to it so the robot can hear it. I'm going to create this message. And then I'm going to go basically step through a couple different joint angles and make the robot go to those. So let's give this a shot. So it's just going to move around a little bit. Nothing big here, right? This is not impressive, like, oh, the robot just moved around. Big deal, right? So yes, this is true. We can actually make this a lot more interesting very, very quickly with ROS. So lesson 2, let's wire this puppy up. So instead of just sending it messages to move around, to move to these different joint angles, what if we actually run it off of one of these things? I think you guys are all familiar with these from playing with PlayStation. So to do this, ROS actually has a package that runs that allows you to set up joysticks, or set up a joystick. And what this package will do is you spin it up. It'll publish joystick messages to a topic. I'm going to write a node that reads the joystick topic and then publishes to the robot topic. And basically says, whenever you hear this, move the robot like this. And you can do that really, really quickly in ROS. So to give you an example here, all I'm doing is I'm pulling in that I'm going to create another node. And so this node is going to use the same messages, and it's going to use this new message called joy. And so this new node is actually a class versus just a little tiny script, because it's going to be running sort of indefinitely. And so all I do is I set up, basically this thing runs indefinitely. Here's a shutdown method. So when you shut down, bring the robot to a nice neutral state. Subscribe to both the joystick state or the joystick message topic, and also to the robot state topic. That is to say, whenever the robot's position changes, just make sure you check what it is. And then basically you send this thing into an infinite loop waiting for the callbacks of both the joy state, right here, and of the robot state. So if we look down here in this method, the robot will basically get its update state. And over here, this is what happens when you actually tell it to move via command from the joystick. Basically, what I do is I look at the current state of the robot. If it's not there, I set it. I create these variables for each of the motors, 1, 2, 3, and 4. And every time the motor gets an update, I basically increment the position of the motor. So if I hit up over here, basically what happens is that I get a little up signal, or just move one of these servos just a little bit. I then do some bookkeeping to clean everything up here. Check to see for changes in the robot's status. So don't move the robot if there's no changes to be done. Don't send a message. And if there is a change, I basically publish that position out, just like the last example I gave you. And then finally, I wrap up with a little bit of bookkeeping. I basically say, hey, if you shut down, send the robot to a neutral state. And if this is an executed node, spin up the node. Then what I have to do is I just add a couple lines to that launch file that I showed you before. So here, I had another node called Joy. It's called Joy node, and it just runs the joystick. I set a couple of parameters, where to look for the joystick, where the dead zone is on the joystick, and how quickly to repeat. And then I spin up the node we just wrote. I just say, start this node. So let's give this a shot. Kill this. Cross launch. Oops. All right. So now I can move it around with this thing. Okay, so that wasn't too bad, right? Not bad for 15 minutes of coding or something. But this is still only kind of interesting. So let's keep pushing it a little bit, and we'll get to something interesting by the end. All right, so I've shown you publish and subscribe primitives, but ROS also has different primitives for doing different robot behaviors. So there are basically built into ROS, sort of built on top of the publish-subscribe model, are basically services and actions. So a service is something where you go and you send a message, something happens, usually fairly quickly, and then a response comes back. That's it. But you only need to do it once or every once in a while. An action is a fairly more complex thing, so you can think of this as your robot doing some sort of interesting behavior. And so an action, you send a goal. You say, robot, I want you to move over here. I want you to do this thing. The robot will send you periodic updates while it's doing that, and then it'll send you basically the end state. And your node can preempt that goal behavior. So if the robot's moving towards some goal and it's going to crash into somebody and flail and burn up, you can actually hit cancel and it'll go away and it'll stop doing what it's doing. And so both of these use the ROS message generator, which is basically this nice bit of code that allows you to intersperse all these C++ and Python calls. So for this example, what I'm going to do is I'm basically going to teach the robot how to, whenever I touch a button on the joystick, how to go to a particular position and record that position. And then for another button on the joystick, I'll create an action. So when I hit that action, it'll replay all of these waypoints that I give the robot as it's going along. The bit to know here is that I have to define my messages in a little bit of YAML. So for the service, all I'm saying is take in a string. The string will be the file that you want to save everything to. And then return a result. Just tell me what happened. And for the animation player action, what I'll take in is a file name and a step size, which is basically how long to wait before playing each command. It will return a result, right, which is just a string. Hey, I did it. No, I didn't do it. This thing happened along the way. And then during the course of the process of playing the animation, I'll basically get an update string of what the robot's currently doing. To make all of this work, I need to do a little bit of modification to make sure C++ knows about it. It's basically setting up a couple lines in a CMake file and in a package XML file. And I need to run catkin, which is the ROS build utility. I'm not going to do that here because it takes a second. But it's fairly straightforward. So why don't we take a look at that code for this ARM controller. And so this is going to be exactly like the thing we just wrote. It's going to be this Python class that's running and has this running process. And what you do is ROS basically imports this ARM message, the service message, which is going to be the service, which will be the waypoint service. And then it'll also, from this OWI ARM message, it'll import the action messages. And so here we create our node. On initialization, we get some params. This is one of the utils in ROS, basically, is to be able to get params from the ROS system bus. So one of the params I'm setting is where I want to save this animation file, which I'm saving it on my desktop. Next thing up is when you get a waypoint, right? When this waypoint service starts, it's going to be called waypoint. You'll get a waypoint message, and you will make a call back to this function. You will also subscribe to the robot state and the robot position stuff, just like we did before, just like we did in the last node. And finally, you'll create what's called an action server, and the action server will actually replay the animations. And all this says is you're going to have something called play animation. It'll take a play animation action object, and it'll execute this callback. So here we go in a state update, just like we saw before, coming from the robot. A spin utility, which basically keeps this process going the entire period. And finally, handle save state. This is where we actually save the state to the file. So all this is getting the input message, looking for the file name inside this request thing, which is passed in, saving that file out, or creating that file if we need to, and then creating a return message. The play animation state will also just be almost nearly identical, right? I have this goal message that comes in. From that goal message, I get a file name, and I get a step size, and I basically play the result. And what I do is I just check. So if I check and the file's not there, I create this result message, and I say, I could not find the file. Pass it back to the robot, the thing that called me. Otherwise, I continue. I load up that file, and then I start playing all the way through. So once I play it, I just say, go here, wait, go here, wait. Okay, so to deploy that onto the joystick, it's very, very simple. It's very similar to creating the main node. In just time, I might skim over this a little bit, but all I do is I bind these methods that call these functions, and I create the messages that go with them. And then I just add this one line back into my launch file. So all of this ends up looking like this. So now what I can do is if I push here, I'll record a waypoint, record a waypoint, record a waypoint, and then I can go and play them back. Right? All right, so we've built up some primitives, right? So the robot's moving around. We're able to do something slightly more complex, but the robot has no feedback. Right? The robot's just flailing around in the middle of space, have no idea where it's going or what it's doing. So we're going to add cameras to this robot. Oh, one last thing. I know this looks cool running in the shell, but we want all this stuff to run on the web. So there is something to check out when this is all over called Robot Web Tools. Basically is a bridge between the ROS message bus that I've been playing on and JavaScript. So you can basically build little JavaScript apps that run on top of your robot. Lots of fun. You should go check it out. Anyway, so now we're going to give our robot some information, some feedback. We're going to give it a camera. And in ROS, running cameras is like the easiest thing in the world. I have run everything from $10,000 FLIR cameras all the way down to $20, like this little piddly camera up here. They almost all work. They generally work pretty well out of the box, and I have never seen such a large diversity of hardware that you can just sort of plug and play. I mean, Velodynes, laser scanners, all the cool toys that you could ever want are in there. ROS cameras talk over a message image, and they're basically published over the message bus, and you can basically marshal them in and out of OpenCV. And they use nodelets, which are sort of like ROS nodes, but they basically allow you to do all your processing without moving whole chunks of memory around. You can just move a pointer around. So to do this, you basically do sudo apt-get install ROS Indigo USB cam and ROS Indigo image proc. Image proc gives you all the tools to do rotation, scaling, that sort of thing. You can also set up a different kind of camera. So here is what launching a camera looks like in ROS. Basically, you create a camera object. You tell it, I want it to be this big. I want it to be this wide. I want it to go this fast. I want it to use this calibration file. And then right here is just some code that basically spins up a couple of views of the camera. So let's do this. If I can spell. All right, so if you guys can see here, this is my camera over here. And so it's just streaming automatically, simple launch file, works right out of the box, app-get. No Python here, but we got a camera, it's running. So I would be remiss if I didn't show you how to do some image processing on this in Python. So why don't we go take a look at that. To get images into Python from this bus, what you're going to use is something called the OpenCV bridge in ROS. And what it does is basically takes it off the bridge, marshals it into what's called a CV2 NumPy array, which is basically a fancy wrapper on NumPy for images. And that's it. So what I'm going to do here, just as a toy example, is I have this red milk cap that I brought in from my milk earlier. And so I'm going to go take this milk cap, and I'm going to teach the robot to find it. And what it's going to do is it's going to search the image, find this, draw something over it, and then it's going to output its pixel position and its size. All right? And so this is a super easy Python script to write in ROS. All I need to do is import this CV bridge, import the point and image messages, which are ROS standard messages. So ROS has got all these geometry messages. It's also got all these basic wrappers around sensor messages. And then some other bookkeeping. I'm going to use SimpleCV because I wrote it and I like using it. And so here's our image processing example class. And all this is, same init string, create a CV bridge, set up my input topics, which I'm going to look for messages in camera image rect color. Image rect color means I want the color rectified image, which is if you have a fisheye camera, rectification is the thing that makes all the lines look straight again. And then I'm also going to get a parameter saying where I want you to output my position stuff. And then I'm basically going to create a publisher, which is the output image, and another publisher, which is the output position. I just say I'm going to put positions on this topic. It's going to be a point type. And then I'm going to subscribe to the input camera message. So I just say I want to look at this input topic. It's going to be an image. And when I get an image, call show colored stuff. Spin my node up to run. And then our only callback is this show colored stuff. So we do basically the message marshalling. Then we move all this into a SimpleCV image. I do a copy. Here is all of my image processing. So all I'm doing is basically a hue distance, which is looking at color, which is saying find something red. I do a connected components, which is basically threshold into a two-tone image. Find the biggest thing that is red, and then give me the position of it. Draw that thing that you found with a yellow overlay right here. I basically take the position of the thing that came out of SimpleCV, the blob, give it a position and a size, and then I publish it. And so, and then a little bit of boilerplate. And so if you watch this, oops. All right. So now it's going to spin up one window, and I might need the lights for this. We'll see. So here's my red bottle cap, and here, hopefully, please work. I might get it. I might need the lights. Or I might be able to use my flashlight. Oh, find it. There it is. So if I go switch over here, I can actually tap directly into the ROS message bus. Oops. Oh, no. So here, I'm going to have ROS actually tell me every single topic that's being published right now. And I can see down here in the bottom, hey, here's a position message. Wonderful. So if I go ROS topic, echo, flash position, it'll actually give me the centroid of my red thing. So I grab this. Let's see if we can do this side by side. Here we go. So I can actually get the position of this thing running around, and it's a message. So if you're building a little toy robot at home, this is great, right? You can just give this to a kid as a package, right? And you can say, go learn to teach your robot how to make follow a red ball, or some sort of trivial task like that. All right, so we got some basics. We have some input, we have some output, we can control the robot. Would you guys like to start doing something interesting, like actually having our robot figure out what it looks like? All right, so I'm going to talk about what is called in ROS and some other sort of paradigms, it's called an URDIF, right? It's Swedish. It stands for Universal Robot Description Format. And what URDIF is it's basically a pile of XML that defines the geometry of your robot. So it says, hey, the robot's got an arm here. Hey, the robot's got a motor here. This is what my robot looks like. This is the joint upon which it moves. This is where my sensors are. And it allows you to do constructed sort of thoughtful geometry about how all this stuff works. And what's great about ROS is that there's actually exporters in CAD for this. So I can actually go to SolidWorks, take my robot model, and export it. I did not do that for this robot. I did this by hand. But I did this by hand so I can show you what it looks like really, really quickly. So robots are made out of joints, right? These rigid bodies that are connecting things, and joints, which are these things that are moving around about an axis. So what the ARvest does is basically allow you to define your joints and then define your links. And so it looks just like this. So just a pile of XML, I say, hey, the robot's base, the bottom base here, is just about this big. Then there's another link right here, which is the first piece of the arm. There's another link up here, which is the second piece of the arm. And then there's another link up here, which is the third piece of the arm. And then there are joints, which are the joint right here, the joint right here, the joint right here, and the joint right here. And I just define these in XML. It's kind of tedious, so I'm not going to go through it, but you just can go and do that. And what you end up with is being able to render a model of your robot by just adding a few simple lines back to your launch file. So all I say is, hey, I want you to take this robot description format that I just wrote and spin it up and put it inside of this visualization framework for ROS called ARvest. And so if you do this right and you make your perfect incantation, it will start looking like start looking like this, right? So now I actually have a model of Twitchy. Now, so this isn't perfect, right? But it's an approximation, right? So I can move him around. I can do this. I can go like this. I can actually look at where all these joints are. So that's cool, right? We can see our robot. We think we can probably figure out some really cool stuff from this. But we need to wire it up to Twitchy, right? So you guys want to wire this up so that it matches what's going on here? Yeah. All right. So the way you wire this up is you actually create what's called a joint state publisher. So a joint state publisher basically is saying, hey, you named all of these joints here. So I'm to just publish their position, and I will actually make the model match what you tell me to. Because I don't need to know where everything is. I just need to know where these key parts that move are. So to do this, I create another node. This is called Joint State Republisher. It's got a couple little parameters in here that I use to tweak stuff. And it's also got what's called a TF listener. And it basically listens to the robot output, the robot status output, and also listens to, can send messages to where the robot should be. And it also has another topic called the joint topic. And we publish to the joint topic. We say, every time the robot updates, your joints are here, your joints are here, your joints are here. And basically ARvest is sitting there listening to where all these joints are and rendering that. It says, okay, my joints are here, make it look like this. My joints are here, make it look like this. So to do this, you basically wait and you create a callback method for every time the robot pushes its joint state. And here is where that happens. Actually, down here is where it happens. So all I do is so this is a little bit of code. This is a little bit more advanced. I'm going to skip over it. But what it does is basically make sure that this head is always facing down. But what I do is I take the input message position. I convert it from radians to, or from degrees to radians. I do a little bit of math on it. I set that up, and I basically create this joint state message here. And I give it each of the joint names, and I set each of the joint values, and then I just publish that. And that's it. And then to construct this into our launch file, we just add a couple more lines, right? So we already have the ARvest stuff in here. We already have all the other stuff we've already written. I just spin up this node, which is right down here, which is the ARM controller. Or wait. It's a joint state publisher. So let's see this running. Good morning. So now we can actually have a robot that matches what it's doing in here. Thank you. Now it's getting impressive. All right, so the guy up front is going to tell me I am running a little bit late. So the next bit of this is, how about we wire up this camera that I set up? to do something actually interesting with this. So let's put all this together. So we have this like intuitive notion, right, that if I have a camera up here, and I have a robot, and I know, and the robot knows like where the camera is, and we know where the robot's arm is, we can kind of like figure out where each pixel kind of maps to in a scene. Not always exactly, there's a whole bunch of math why you can't always do that correctly and how. You have this sort of intuitive notion, and you'd like to be able to tell the robot where it is in the world. And so what I've done here is I'd like to be able to tell this robot where it is with respect to my whole world and tell it where certain things are. So one solution to this is that I could like sit here all day with a yardstick and a tape measure and figure out where all these things are and measure like how far this camera is from this joint and all that kind of stuff. But we're lazy software engineers. I don't want to do that ever, right? So there's actually a couple packages I can lean on to solve all of these problems for me. And so what we're going to use is what are called AR markers. And so what we're going to do is we're going to use the camera to find these AR markers. And so these are like super high contrast, big patterns that you can do image processing on pretty quickly. You know how big they are. You have a bunch of points on there. And so you can actually figure out where the camera is positioned with respect to one of these. So if the camera sees this and the camera's calibrated, it can say, oh, I'm here with respect to that. And I can also say, oh, the camera's with respect to this is over here. So I can do the inverse transform. And I can also tie that transform to other bits in the scene. So I can actually tie this guy to sort of this AR marker that's holding off behind the robot. And this is just a package in ROS. Like, this is like, okay, this one I had installed from source, but it wasn't a big deal. You use what's called WS tool. So you just say WS tool, get this package from Get, and build it. And then you just do some configuration, right? So I just added a couple lines here to my launch file. Basically say, hey, robot, TF. Between you and this marker is this far, and the rotation from this marker to you is like this. And then I fire up this AR toolkit marker package, and it just runs. It basically sucks off all of the data from my camera, goes through, figures out where its position is with respect to this marker, and shoots that to ARvest to say, oh, you're here. There's a little bit of configuration I have to do here where I say, I'm going to use 3 markers. All right, so why don't we take a look at this. I'm going to need the house lights for this if that's possible. Let's see. Okay, so this won't actually spin up until it sees, if I can get the lights here, hopefully this will work. So this won't spin up until it actually sees the marker, but if I use this, there it goes. So let's take a look at this. So what you can see is I know where the image is, I know what's in the image, and I have a model of my robot. Here we go. And now what I can do is I can actually project my robot model onto my imagery, which you can see where this could get kind of useful, right? Because now I can find these other little markers, right? If I were to put them on, like, say, boxes or things my robot wanted to pick up. And can you find it? Maybe. So if I have a marker for here, right, and I have a marker for the robot, and I know where this is to here, and I know where this thing is in my entire scene, ROS makes it super simple to figure out all the math here. So I can basically say that the position differential, the difference in position between the tip of my robot right out here and this thing that I laid in the scene, I can figure that out all in a function call, which is pretty sweet. Let's just take a look at this a little bit more in case you guys didn't see this. It's moving around. And so in ROS, what I can do is I can make a single function call here to TF. And so TF is this library that says, give me the position from A to B. So for a marker that's sitting in the scene all the way to the end effector of the robot, single function call to know the position difference and the rotation difference between these two. So in Python, that looks just like this. And we can also run it in the command line. So I'll do that really quick. Hopefully this works. Hopefully you can see the right marker. And so this is actually the position difference between this marker and the end effector of this robot. And that's a function call in Python, and that's it, which is pretty powerful. All right, so last little bit here, and I'm not going to show all of this, but I just want to show this as a taste of what's available to you, is that there's finally a ROS package called MoveIt. And what MoveIt does is it's your inverse kinematic solver for this. So if I have this position right here, and I know what my robot looks like and where this is here, this inverse kinematics package, its job, this is the hard math of robotics, is basically go from here to here. And so I ran a little bit late, so I have to wrap up here, but if you guys are interested, come talk to me. Thank you.